Excuse me. So these permanent magnets, these permanent dipoles, attract each other because we have a positive end and a negative end. And so those positive and negative ends attract each other. Polar molecules have higher melting points and boiling points relative to nonpolar molecules of similar molar mass, which is because of their permanent dipole, but also stronger intermolecular forces. So an example of a polar molecule, formaldehyde is polar, and so it has a permanent dipole. So what that means is that the oxygen side, so this is oxygen, and this is hydrogen, and the black one there is carbon. So if you remember back to before spring break, you know that vague time before spring break, oxygen is more electronegative than carbon, and so it's going to be hogging more of the electrons, and those electrons have negative charge, and so the oxygen is going to have this permanent partial negative charge. The opposite side of that molecule then, where these hydrogens are attached to the carbon, carbon is more electronegative than hydrogen, so carbon will have more of the electrons than the hydrogens, and so those hydrogens will have this permanent partial positive charge. So you can think of these as magnets lining up, negative charge to positive charge, and then this negative charge could line up with another positive charge, and so on and so forth. And so they would stick together a lot better than if they didn't have this permanent dipole. So this affects our melting points and boiling points, as I mentioned before. But here we can see that we have these two molecules, formaldehyde, so this is the one that we had on that previous slide, and we have ethane. Both of these have molar masses of about 30, but the boiling point of formaldehyde is negative 19.5, whereas the boiling point of ethane is much lower. So that means that at colder temperatures, it's already boiling into a gas at negative 88 degrees Celsius. And the melting point also is higher for formaldehyde, meaning that it takes more energy to overcome those bonds to melt solid formaldehyde into liquid formaldehyde, and also takes more energy to boil that or vaporize that liquid formaldehyde into gaseous formaldehyde. So again, all of this comes back to the strength of these intermolecular forces. Another thing I want to add here too is that these intermolecular forces are additive, meaning that if you have more than one of them, you can sort of add their strengths together. And that's kind of another way to think about it, because everything has dispersion forces. So our formaldehyde here, if I can spell properly, dispersion, has dispersion forces, and it has this new one that we're talking about, the dipole-dipole. Whereas ethane only has dispersion forces. So formaldehyde's got two different types of force going for it, whereas ethane only has one, in addition to that being a weaker force. So again, it's our polar molecules that have dipole-dipole forces, and this affects miscibility, which we did talk about a little bit here. For me, I remember miscibility, and every time I see it, I remember this as mixability. So it's the ability for two liquids to mix together. Similar to if you put salt in water, it'll completely dissolve. If you add two miscible liquids, they will completely combine, and you won't be able to tell one apart from the other. There aren't many, really, in your home, there aren't that many liquids that you deal with. that you would mix together in this way. If you wanted to try one, you could take isopropyl alcohol and you could mix that with water. Those two liquids are miscible. And so these polar liquids, isopropyl alcohol is polar, and so is water. So polar liquids are miscible with other polar liquids, but they are immiscible or not miscible with nonpolar liquids. And this is the like dissolves like. So if you have a polar liquid, it will be miscible with polar liquids. If you have a nonpolar liquid, which would be oil, like canola oil, vegetable oil. Canola oil is nonpolar. And so this is why you can mix different types of oils together also, right? Because we have canola oil, but you also have olive oil or even avocado oil now. Although that's less expensive. So our oils are nonpolar. Things like water are going to be polar. The key thing here is like dissolves like. It's all right. Let me know if I need to spend more time on each slide. I don't know if we'll be able to see if you like use the hand raise function on Zoom. But actually, can somebody try that for me real quick? If you know how to do that, if you click on reactions. I see a thumbs up. Okay. Yeah, that does work. So I will be able to see those. Claps, thumbs up, and hand raises. So just let me know if you have a question or if I need to slow down. Which I think there's a slow down reaction too, isn't there? Yeah, slow down. I was about to quote an inappropriate song. Pentane, so some examples of these liquids. Pentane is one, is a nonpolar liquid, will not mix with water. So you see that here. I could show you that in the lab if we were there. Oil and vinegar. Vinegar, if you didn't know, is actually mostly water, but the acetic acid in there is its own liquid. The acetic acid in there is a liquid as well, but it mixes with water. But oil and vinegar don't mix, which is why you have to shake it up every time you want to use a vinaigrette. Is there a question? Or is that just a hand up from earlier? I figured, I hovered over it and it said, I'm away, but I figured it was because I was drinking coffee. All right. So an oil spill from a tanker also demonstrates this. The petroleum or crude oil, depending on what it is, will float on the surface of the water, which is a huge problem for any wildlife, especially, or sea life, I should say, that either surfaces to breathe. So, like whales have to surface to breathe. When they come to the surface, they're going to get that oil and it's going to stick to their skin. Birds also landing on the ocean will be coated with oil and then not be able to fly because that oil sits right on the surface and doesn't mix. So again, polar molecules, let me write this up here also. Polar molecules have dipole forces. Dipole intermolecular forces. There are a couple ways you can determine this. This is also exactly the same thing that we talked about with Lewis dot structures in relation to polarity, right? We did Lewis dot structures and then looked at whether they had, well, really you look at the molecular geometry and see if it's asymmetrical, or you could just look and see if there are lone pairs. But this is the same thing. We're just kind of bringing it back up here because it's important for knowing which types of molecules have dipole-dipole forces. So in the book, the method they use is to determine whether the molecule contains polar bonds. So that would be sort of knowing the relative electronegativity of those bonds, whether one atom is more electronegative than another. One example would be something like HCl. Chlorine's on the right side of the periodic table. It's a halogen. It's more electronegative than hydrogen, so this would be a polar bond. And then you determine whether the polar bonds add together to form a net dipole moment. This one gets a little bit more difficult when you have molecules that are three-dimensional. Some of the more complex geometries are hard to visualize. I like my mom's method better, which is a molecule is nonpolar if both conditions are true. So this is, there are no lone pairs on the central atom, and the atoms bonded to the central atom are identical or have the same electronegativity. For the most part in this class, if all of them are identical, it's going to be nonpolar because they'll probably have the same, well, if they're identical, they do have the same electronegativity. But most of the time they're going to have the same or similar electronegativity. If they're different, they will have different electronegativities. So an example of this would be like CH3Br. So we'd have 3 hydrogens around our carbon and 1 bromine. So that bromine, again, is more electronegative than the hydrogens, so this would be a polar molecule. So if these are not all the same, and there are no lone pairs, then it's going to be, sorry, I said that wrong. If there are no lone pairs, and the atoms are all the same, it's nonpolar. If either of these is false, then it's going to be polar. So if it has lone pairs, it's polar. If the atoms bonded to the central atom are not the same, it's polar. Maybe we have some examples here. So do you have a Minty quiz for this one? All right, so, oh wait. Do I not? Oh yeah, I do, it's this one. Did we miss one? Huh. Okay. So we want to determine if each of these molecules has dipole-dipole forces or not. So remember, dipole-dipole forces means we have a polar molecule. So we need to look at each molecule and see if it's polar. So the way this Minty quiz is set up is if it's 0, it has no dipole-dipole. If you move that slider over to the right, that means it has, or that means you think it has dipole-dipole forces. So you can choose sort of either 0 or 1 for each of these. So what I would suggest doing for each of these to start is to write out a skeletal structure just like we would have done for Lewis dot structures. So for Ci, that's an I there, Ci4 carbon tetraiodide, we're going to have C. Actually, I need a little more room than that. Carbon, and then we're going to have the 4 iodine atoms surrounding that carbon. And from there, we can look at it and see, well, do we need to go any further and draw out the rest of this Lewis dot structure to determine if it's polar or not? Or can we see from here if it's polar? So, was there a question? Oh, go ahead, go ahead. Yeah. Right, correct. Yeah. So this one's nonpolar because there's no lone pair and then all of the atoms attached to carbon are identical, or the same. So if this is nonpolar, then is this, I'm going to write this on here, nonpolar. Does it have dipole-dipole forces, or are there no dipole-dipole forces? And again, you can go ahead and vote on the Mentimeter quiz, or Mentimeter website app. Should figure out what I'm going to call it. Oh, we got one vote. Oh, I guess we have to go. I guess, yeah, you can't just enter just one, so I guess we'll keep moving. Sorry about that. Okay, for CH3Cl, again, we'll draw this out the same with the skeletal first. So this is going to be 3 hydrogens and a chlorine. So is that molecule polar or nonpolar? So again, here we have no lone pairs, but unlike the Ci4, we have chlorine and 3 hydrogens. So these are not all identical, and chlorine is more electronegative than hydrogen, so this one is going to be polar. And then for our last one here, before we get into the dipole-dipole or not, we'll have HCl. And here we have just a binary molecule, or we have a molecule with just 2 atoms. So we can just look at the relative electronegativity between these two. And chlorine, I mean, hydrogen's basically the least electronegative, and chlorine is going to be fairly electronegative. So this one's going to also be polar. Yeah. Yep. Yeah, whatever's closest to, so fluorine is the most electronegative. So if it's closer to fluorine, it's more electronegative. Mm-hmm. Yeah. So we got some votes in there ahead of me drawing out the rest of these. But it looks like kind of ish on the right track. Seems to be some confusion still. Hard to say, and actually maybe I should just reset this slide and we can... Can I reset this slide? Oh. Okay, let's do a reset real quick. And we can do a quick revote, hopefully. Kind of wish I had the option here to like have anonymous comments, but that's okay. Oh yeah, I can do a countdown too. Remember, this is A and B and C. So the key for these is that if we have a polar molecule, then we have dipole-dipole forces. So for CHI4, that's no dipole. And then for our 2 other ones, they're both polar, so they both have dipole forces. So if it's polar, it has dipole forces. If it's nonpolar, it does not have dipole forces. Oh, the website and the ID again? Here you go. I know it can be kind of small on the top of the screen there. Okay, we're going to move on, though. All right, so we determined those dipole-dipole forces. So now we're moving on to a stronger force than dipole-dipole forces. And this is a special one, and it's called hydrogen bonding. So we started with, and I'll do it like this. So if this is the weakest, and then we put strongest. Our weakest force is dispersion. Then stronger than that is going to be our dipole. And now hydrogen is going to be not the strongest intermolecular force, but it's up there close to the strongest. So hydrogen bonding occurs with hydrogen, and specifically it occurs in polar molecules that have hydrogen atoms, and this is the key, hydrogen atoms bound directly to fluorine, oxygen, or nitrogen. So this additional intermolecular force, because remember, these add on top of each other. So if something has dipole forces, that doesn't mean it does not have dispersion forces. If something has hydrogen force or hydrogen bonding, it also has dipole and dispersion forces. So our hydrogen bond is a sort of super dipole force. This happens because there's a large electronegativity difference between hydrogen and these three electronegative elements in particular. The small size of the atoms, that's when it says these atoms, that means fluorine, oxygen, nitrogen, and hydrogen, right? They're all very small atoms, very close to the top of the periodic table. It allows neighboring molecules to get really close. And really what this means is there's a large difference in electronegativity between like hydrogen and fluorine is one of the places we can have hydrogen bonding. So most of the electrons, if we're to visualize those sort of with an electron cloud, most of those electrons are going to be around fluorine. So that's going to have our partial negative. And then the nucleus, which is positively charged, the nucleus of hydrogen will be relatively exposed. And so that can get really close to another fluorine with its hydrogen, where this fluorine again is very electronegative. And you get almost a pseudo bond between fluorine and hydrogen of a separate molecule. And again, this is an intermolecular force, so it's between two separate molecules. Now, I say it's a pseudo bond because hydrogen bonds, and it can be confusing because they're called hydrogen bonds, but they occur between molecules, whereas covalent bonds occur between atoms within the same molecule. So hydrogen bonds are much weaker than covalent bonds, typically 2 to 5% of that strength. So while these are still weaker, I can do another one of these. So like weak and then strong in terms of bond strength or intermolecular force strength. Over here is dispersion, dipole-dipole, and then hydrogen bonds are quite a bit stronger, but still not nearly as strong as covalent bonds, which are actually actual bonds occurring inside of a molecule. So for hydrofluoric acid, HF, the hydrogen in each molecule is strongly attracted to the fluorine on its neighbor. Again, so you get them lining up like this. And you get this very strong intermolecular force between the separate hydrogens and fluorines, the hydrogens and fluorines of separate molecules. So it is in a way a dipole-dipole force, right? Because we have the partial negative and the partial positive. But because these are such small atoms, they're able to get closer. And if you've ever played with magnets, you know that the closer the magnet gets to something that's magnetic, the stronger that attraction is. So if we can get these charges, which are different, closer together, they're going to be attracted together more strongly. So something like methanol has, and again, this is the key here, hydrogen directly bonded to oxygen, and this can be oxygen, fluorine, or nitrogen. But here we have it directly bound to oxygen. The methanol molecules can form hydrogen bonds to one another. So the hydrogen atom on each methanol is attracted to the oxygen atom of its neighbor. And that's what we're seeing right here. So anytime that you have hydrogen directly bound to oxygen, fluorine, or nitrogen, you're going to have hydrogen bonding, and that's going to be stronger than dispersion forces or regular dipole-dipole force. Okay, so we have two molecules again. Remember, we compared to a polar molecule and a nonpolar molecule of similar molecular weight before. Here we have a polar molecule that has hydrogen bonding, mass of 32, and comparing that to ethane, which is a nonpolar molecule. So it doesn't have dipole-dipole, it does not have hydrogen bonding, and it has a similar molar mass of 30.1. And this is how significant this is. So formaldehyde was our one from earlier. Do I want a page back and try and find it? What slide are we? 69. Negative 19.5. So formaldehyde was negative 19.5. Make this a little bit easier to see. Degree C, degree C, degree C. So basically, right, think of the boiling point. It's a liquid below that temperature. So below 64.7 degrees C, methanol is a liquid. Below negative 19.5 degrees C, formaldehyde's a liquid. And then below negative 88, ethane is a liquid. So there's a very, very large difference in the boiling points of these liquids. There's also a large difference between the melting points too, so where they turn into solids. And this is because methanol has, not only does it have hydrogen bonding, it also has dipole-dipole, and it has dispersion force. So it has all three of these together, whereas formaldehyde just has dispersion and dipole-dipole. And ethane only has dispersion. I think another way you can think about these is that dispersion forces are kind of like a glue stick in terms of how sticky they are, right? Glue sticks, they like work mostly, but they're not great. Dipole forces here is kind of like moving up to like Elmer's or like gel glue, like liquid glues. They're much stronger than the glue stick, but they're still not as strong as using something like super glue for your hydrogen bond. Right, so these are, and then this is like using a glue stick, Elmer's wood glue or something, and then super glue all together. And well, actually, I think if you actually did that, you wouldn't get as strong a bond, but right, adding up those sticky factors together, this hydrogen bond plus the dipole-dipole plus the dispersion is much, much, much stronger than dispersion forces at holding these individual molecules together. And the big takeaway I want you guys to understand here is the relative strengths of these intermolecular forces. And then to understand that those intermolecular forces determine things like melting point and boiling point. We have, to continue on this thing with hydrogen bonding though, water is especially good at hydrogen bonding. This is because each water molecule has 2 hydrogens directly bound to oxygen. So you can essentially get twice the amount of hydrogen bonding. So this makes the boiling point of water 100 degrees C, which is higher even than methanol, which was like 60 degrees C, even though water is almost half as massive, right? It's half the weight, but it has a higher boiling point, almost double the boiling point. This is because not only does it have dispersion, because everything has dispersion forces, it also has dipole forces, dipole-dipole, and it has hydrogen bonding, basically times 2. Sorry about that. All right, so this is a lot of intermolecular force. This is like using twice the superglue. When it comes to DNA, hydrogen bonding is actually what holds DNA together, the separate strands of the helix. The base pairs that code your DNA have hydrogen bonding sites so that they can hydrogen bond with the opposite base pair, which I think is pretty cool. All right, here's the next. Oh, I think this is what I did. I had them out of order here. Yeah, this is the one we skipped. So let me go ahead and reset this. Okay, so reset the slide. So we're looking here at, and actually before even that, we have several different forces going on here. Oh, and I can pull this up too here. There we go. We're on the Mentimeter quiz. So remember, we have dispersion, dipole-dipole, and hydrogen bonding at this point. So when we look at HF, hydrofluoric acid, compared to hydrochloric acid, we have to basically decide which of these has more intermolecular forces and more stronger intermolecular forces than the other one. So place your votes now. Yeah. Uh-huh. All molecules have dispersion forces. Mm-hmm. Yeah. Yep, it is. All of them. All right, here, I'm going to start a countdown. You got 1 minute to place your votes. So really looking at the relative strength of different forces here. Maybe 1 minute was too long. But it'll let me rest my voice for a second. There's 5 more people who haven't voted. Unless there could be people doubled up in the chat here. I see 2 iPhones that don't have names, so it could be the same person. Okay. So as voting closes here, there are, let's line up these. So everything has dispersion forces. So both of these have dispersion. Both of these are hydrogen, which is not very electronegative, with fluorine, and then hydrogen with chlorine. And chlorine and fluorine are both very electronegative. So they both have, they're both polar, so they both have dipole forces. And then our last force here is hydrogen bonding. So hydrogen bonding is stronger than dipole-dipole, and it's stronger than dispersion. And the key there is that you have to have hydrogen directly bound to nitrogen, oxygen, or fluorine. So here we do have fluorine, right? We have fluorine and we have hydrogen directly bound to fluorine, so we're going to have hydrogen bonding here as well. But we're not going to have hydrogen bonding for HCl. Now, if you were to look at just dispersion forces, HCl would have, or does have stronger dispersion forces, because HCl, particularly the chlorine, is a larger atom, so it's a larger molecule. But that increase in dispersion force is very, very small. And the dipole-dipole forces here are going to be roughly the same. But the hydrogen bonding, having hydrogen bonding versus no hydrogen bonding, really is what makes the difference. So this would be like using a little more extra glue stick compared to using super glue here. Right? The super glue is going to make a much larger difference than adding a little bit more glue stick. But I definitely understand why some people have voted for HCl. If this is what you were thinking, the dispersion forces. Oh, and sorry. The question here is specifically which has a higher boiling point. The molecule with the stronger intermolecular forces is going to have the higher boiling point. So that's kind of why you can answer the one question with another question, or by answering a separate question. Okay. So you might think super glue is the strongest. It's actually not the case. We could use like epoxy or CA glue or liquid weld or JB weld. And that's our ion dipole force. So ion dipole forces are a special type of intermolecular force that occurs in mixtures of ionic compounds and polar compounds. So these are especially important when you have an aqueous solution of an ionic compound, which is a mixture of something like water, right? Aqueous solutions have water, or water solutions. So when we have sodium chloride dissolved in water, we have these negative chloride ions, that's this guy right here, interacting with the positive poles of the water molecules, and the positive sodium ions interacting with the negative poles of the water molecules. So this is an even stronger intermolecular force than hydrogen bonding. But it only occurs between a polar solvent and an ion that's dissolved in that solvent. So solvent here being some sort of liquid. I think my chair's sinking. Oh, I can switch this back. Sorry. Lost my mouse. Okay. So here we have sodium chloride. Again, let me zoom this. So these are all the positive ends of these water molecules surrounding the negative chlorine. And then all of the negative ends of the water molecules surrounding the positive sodium. And this is really the summary and sort of like the takeaway for this section is that we have dispersion forces, which are weak, but can increase with increasing molar mass, although generally those increases are relatively small or small relative to other forces. We have dipole-dipole force, which is a moderate force, and it's only occurring in polar molecules. There's also hydrogen bonds, which are strong and occur when we have hydrogen directly bound to fluorine, oxygen, or nitrogen. And then we have ion dipole forces, which are very strong. And if we want to relate these back again to my silly glue analogy, our dispersion force is a glue stick. Dipole forces are Elmer's glue. Hydrogen bond is super glue. And ion dipole is like epoxy or CA glue, that's what I was looking of. If those aren't super helpful analogies, I will not give you this table on the exam. You need to know which of these is stronger. Yeah. If these aren't super helpful, you could relate these to things like, these are like rubber bands or staples. This would be like a rubber band. This would be like a bungee cord. This would be like a ratchet strap. And this would be like steel cabling or something. But know that these are all different forces that cause atoms to stick together, and they can be ranked based on their relative strength. Okay, so before we move on to there, I do have one more Mentimeter slide here. Yeah. This is a new type of quiz on here that I want to try out. Actually, I wanted to do it on my phone too. Where's my phone? So we want to rank these intermolecular forces based on the strongest. So put the strongest at first, second strongest, third strongest, fourth strongest, and then the weakest as the fifth strongest force. I'll just give this a minute there. Oh, interesting. Ooh. I like this. Okay, interesting. So remember, first place is the strongest type of bond. Second would be the second strongest. Third would be the third strongest. And fifth is the weakest. Okay, interesting. 10 votes here. So dispersion, and maybe you were ranking these because of the way that they were ordered on here. Dispersion force is actually the weakest force. So this one dispersion forces should have been fifth. Then the strongest force is actually, which wasn't on this one, but covalent bonds, which I mentioned very briefly, but those are the bonds that occur that hold an atom or a molecule together, right? Holds the atoms in a molecule together. So this should have been first, followed by ion dipole at second, hydrogen bond at third, and dipole-dipole at fourth. So maybe there was some confusion as to, I don't know if I can get a better look at the breakdown of these votes, show test votes. I think this is showing the votes as they went in. Okay. Yeah, so maybe just spend some time with this in terms of ranking these different types of forces. And maybe I'll make a note to add this to a quiz. So let me do that real quick. Okay. Good to know, though. Unfortunately, we do have to keep moving. So the second to last thing we're going to talk about in this chapter are different types of solids. So we can have, right, we mentioned these at the very, very beginning of the semester, that we had different types of solids. And these molecular and ionic in particular, relate to nomenclature. So the same way that we identified something as molecular or ionic for nomenclature applies here as well, right? So our ionic compounds are going to be metals plus nonmetals, and our molecular compounds are going to be just nonmetals. And then atomic compounds are just consist of a single element. So when we're looking at these different types of solids, we have different ways to name them because they are different sort of in their makeup. And we can have crystalline solids, which are well-ordered arrays of atoms or molecules, or we can have amorphous solids, which have no long-range order. But we're going to be talking about crystalline solids, in particular molecular, ionic, and atomic solids. So we can break those into separate categories in a nice flow chart like this. And the key for these and telling them apart is this center section. In molecular solids, the composite units are all molecules. So something like H2O, right? Ice is made up of individual H2O molecules. Something like sodium chloride, on the other hand, an ionic solid, we talk about those, and I didn't emphasize this very much, but they're formula units. So something like sodium chloride doesn't have individual NaCl molecules, but rather is a bunch of sodiums and a bunch of chlorines bound together at a 1-to-1 ratio. So you would have 1 million chlorines and 1 million sodiums in a crystal of sodium chloride. But there's nothing differentiating any of those individual formula units. We just break it down to the simplest ratio. And then atomic solids, a lot of them are going to be metals, but we can have other types of atomic solids. And that's where the composite units, or the units that make it up, are all atoms of the same type. So pure gold is going to have only gold atoms inside. Graphite, like in your pencils, is going to have only carbon atoms. And then these properties actually kind of relate to the melting points as well. Molecular solids generally have low melting points, right? Ice melts at 0 degrees C. Table salt and ionic solids have really high melting points. So table salt doesn't melt to like 1800 degrees C. It's on the next slide or so. And then atomic solids have very variable melting points. So some of them have very low melting points, some of them have very high melting points. Molecular solids, whose composite units are molecules. So ice or dry ice, they're held together by the intermolecular forces that we just talked about, right? So there are molecules, and those molecules are held together by these forces, either dispersion forces, dipole-dipole forces, hydrogen bonding. Ice is held together by hydrogen bonds, which is why it melts at 100 degrees C, whereas dry ice is only held together by dispersion forces. So dry ice turns directly into a gas, skips being a liquid altogether, at negative 78 degrees C, whereas ice melts at 0 degrees C. Sorry, I think I said 100. Right, so that's again another example of how these intermolecular forces determine the boiling points or melting points. In ionic solids, which are composed of formula units, the individual atoms of an ionic solid are held together by electrostatic attractions. So between cations, remember those are positive charges, and anions, which are negative charges. So it's like this. Cations are positive, anions are negative. So when we talked about like dipole-dipole forces or even dispersion forces, and we have these instantaneous dipoles, where we had a partial positive, use HF again, right? So this side would be partially negative, this side would be partially positive. Those are only partial charges, whereas in something like sodium chloride, that sodium has a full plus charge, and the chloride has a full negative charge, not a partial. So those are going to be very, very strongly attracted to each other. And they stick together in a three-dimensional array. And again, that's this sodium, chlorine, sodium, chlorine, chlorine. The grid. Because these ionic bonds are very strong, right, high bond strength, they have high melting points. So sodium chloride, it wasn't 1800, it was 801 degrees Celsius. All right, so it takes a lot of energy, a lot of heat energy for that to melt. They actually use, in California, they have, I think, a couple of these where they use liquid salt to capture. If you've ever driven out of Southern California through like Arizona, you've driven past probably those solar collection farms. It's all those mirrors out in the desert, and they're all pointing at a tower. That tower doesn't have water in it. It's got liquid salt. It might not be sodium chloride, but they have molten salt in those to capture all of that heat energy and then use that to boil water in and generate electricity. And then our atomic solids are composed of individual atoms of the same type. So a diamond is a solid lattice or solid single crystal of carbon. Iron, pure iron, would be a single crystal of iron atoms, and solid xenon would be a single crystal of xenon atoms. So we can actually further divide our atomic solids into 3 different categories held together by different kinds of force. So it's going to be covalent atomic solids, metallic atomic solids, and non-bonding atomic solids. I won't linger here too long because these are on the next slide. I should have a mute button so I can just mute for that. So again, here we have our atomic solids, and we're breaking those down further. Covalent solids are atoms held together by covalent bonds. So that is something like silicon, or we mentioned also diamond. They have very high melting points because covalent bonds are some of the strongest bonds that we know of. We also have non-bonding atomic solids, which are just held together by dispersion forces. So this is what Fritz London was trying to describe when he proposed, or trying to explain when he proposed dispersion forces. Things like xenon, essentially the atoms stick together only because of the dispersion forces. And so it takes very, very low temperatures for those solids to form. Metallic solids, and we won't talk about these very much, but they're held together by metallic bonds, and they have variable melting points. Hopefully you can't hear my wife's watching YouTube in the living room. Let me know if you can hear it. So covalent atomic solids are held together by covalent bonds, as the name would suggest, like diamonds. And each carbon atom is forming 4 covalent bonds to 4 other carbon atoms, which is forming 4 more bonds with 4 other carbon atoms. Well, actually, 3 in addition to the first one. But each carbon atom has 4 bonds that are all attached to 4 other carbon atoms in a tetrahedral geometry, which we covered in the last chapter. And so you can think of a diamond crystal as a giant molecule. So you have a giant diamond, that is a single molecule of carbon, which is pretty crazy. So their melting points are very high. Diamond is estimated to melt at about 3,800 degrees C. Very, very high temperatures. If you were to look into at the structure of these of a diamond, they have carbon atoms form covalent bonds in a 3-dimensional hexagonal pattern. So you can kind of see the hexagons in here. I can highlight it right there. So there's one hexagon. It has 6 sides. There's another hexagon here. They're kind of crumpled hexagons. There's another one over here. And so there's this repeating hexagonal pattern throughout the crystal. Non-bonding atomic solids are held together by relatively weak dispersion forces, such as solid xenon. Xenon atoms have stable electron configurations. Remember, xenon's a noble gas, so it has 8 valence electrons. It's not going to form any bonds. And they have very low melting points. And again, this is because the only thing holding the xenon atoms together are dispersion forces, which are very, very weak forces. And then finally, our metallic atomic solids are held together by metallic bonds, which all you really need to know is that they are they're positively charged ions in a sea of electrons. So iron, you would just have a bunch of iron atoms surrounded by electrons all mushed together. Metallic bond strength can vary a lot. which means that we have metals like mercury, which melt at negative 39 degrees C, but also iron, which melts at 1,809 degrees C. So they're variable. So here's a simple diagram. We've got these positively charged ions and all of these electrons floating around, which also explains, there's also one explanation for why metals can conduct electricity, because they have these free-flowing electrons. All right, last Mentimeter quiz for this chapter. So we've talked about these three different types of crystalline solids: molecular, ionic, or atomic. And I'm just going to put a minute on the clock here. And, or I'll put a minute on the clock in a second. So we just want to identify each solid as molecular, ionic, or atomic. And you can use the same rules here that you would for nomenclature. So if you would name it as a molecular compound, then it's a molecular solid. If you would name it as an ionic compound, it's an ionic solid. There's one vote in. Shut the clock here. And again, this is sort of like the last one. So 0 would be molecular, or maybe that's 1. 1 is molecular, 2 is ionic, 3 is atomic. Definitely a little bit split. We're at 5, 3, and 1. 2, 7, 1. 4, 1, and 6. Very divided on that last one. Just a couple seconds left here. All right. So yeah, I would say definitely go back and review these. I think the correct answers here got the majority of the votes. But let's go through these one at a time. So when we were doing these, when we were doing nomenclature, I think I drew out this sort of flow chart for you. Remember, anything atomic solids, that's all elements of one type. So krypton, here, there's only a single element in that solid. So this would be an atomic solid. I wouldn't call it molecular because it's not a molecule. So there's only krypton in there. And the kryptons, actually, I should think about this. How would you know that there are, well, okay, so this is how you would know. Krypton, you can pull up the periodic table briefly here. Number 54 on the, or sorry, 36 on the far right is a noble gas. So it's going to have a complete valence shell, so it's not going to form any bonds. So that would be an atomic solid. I would say to differentiate this from, oh, actually take it back. Yeah, it's an atomic solid, flat out, bar done. I was thinking of, we have 3 different types of atomic solids. We can talk about that more in a second. Going back up to these other 2, calcium oxide is a metal and a nonmetal. So that means that we have an ionic compound, and we would name it as an ionic compound. So this is an ionic solid. And then NH3 doesn't have any metals in it. So if it's more than one type of atom and it doesn't have any metals, and it's just more than one nonmetal, then that is a molecular solid. I don't think I'm going to require you to know how to divide up atomic solids further into the three other categories. We could talk about it briefly, though. So krypton would be a non-bonding atomic solid because it's a noble gas. So it's not going to form any bonds because it doesn't need to, because it's got a full valence shell. If, switch this here, something else, like carbon, so if it was carbon solid, that would be a covalent atomic solid. But also something like oxygen solid would be another covalent atomic solid. And then the way you would identify a metallic atomic solid is if you got iron solid. That would be metallic atomic solid. Are there any questions on these, on identifying different types of crystalline solids? Mm-hmm. If it's any non-metal other than the noble gases. Yeah. So carbon, oxygen, sulfur, nitrogen, I think those would all be covalent solids, atomic solids. But we're not going to go much deeper other than knowing what they are. Are there any other questions? This is the part that I would expect you to know. Not what type of atomic solid it is, just that it is an atomic solid. So, go ahead. Periodic table? Yeah, that can definitely help you out. And I think reviewing nomenclature. So the rules for these again would be it's a molecular solid if it's more than one nonmetal. And then it's an ionic solid if it's a metal plus a nonmetal. Really one or more nonmetals. And it's atomic solid if it's only one element. So it could be a metal or a nonmetal, but it would be by itself. So carbon, parentheses solid, would be an atomic solid. Does that help? Okay. Yeah, sometimes it helps to just put it into like, yeah. There's a lot of stuff that goes on. But yeah, really it does just break down to those sort of three rules there. All right, we got just a few more slides here. And we can finish up chapter 12. Mostly we're just going to talk about water. So water is a remarkable molecule, as the slide says, because it has a low molar mass, and yet it's a liquid at room temperature instead of a gas. So boiling point of 100 degrees Celsius, whereas other molecules that are similarly sized, so H2S, H2SE, or H2TE, which are all in the same column as oxygen, sulfur, selenium, and tellurium. Those are all gases at room temperature. And water is really what allows life to exist because it dissolves many other polar and ionic compounds. It transports nutrients throughout our bodies. And life is impossible as we know it without water. So in most places on Earth where liquid water exists, life exists. And that's why recent evidence of water on Mars, whether it's liquid or not, was very exciting because maybe there's life or was life on Mars at one point. The other place that life might be likely in our solar system is one of Jupiter's moons, Europa. I think it's Jupiter's moon. Because the moon is basically a ice ball with a water core, or at least has a lot of water under the surface, liquid water. And that water stays liquid because of basically tidal forces or gravitational forces from Jupiter itself. So life might exist on Europa. Water also freezes in a unique way. Most substances, when they freeze, they actually get smaller, so they contract, which makes them more dense, which means they sink. Water, though, when it freezes, expands. This does a couple things, right? So ice cubes float, icebergs float. The frozen layer of ice at the surface of a winter lake can insulate the water in the lake from further freezing, which keeps the aquatic life underneath that layer of ice alive throughout cold, harsh winters. On the other hand, the expansion of water upon freezing is one reason that most organisms do not survive freezing, because when water within a cell freezes, it expands and ruptures the cell. So you basically get cells exploding at a molecular level. So a lot of foods, especially those with high water content, this is why they get like mealy when you freeze them, so like fruits and stuff, like frozen fruits. Flash freezing is a process of freezing so fast that water crystals can't form, so the ice doesn't expand and doesn't cause that same problem. My fun, weird aside on this is there's a lot of research done on whether we could freeze humans. I don't know if you guys know this, but like Walt Disney is like frozen just in case. I think they probably flash froze him just in case in the future we could bring him back to life. Like he paid for that. But the microwave oven, the technology in our microwave ovens, was developed to thaw out frozen hamsters. Because they found that using microwave radiation was able to more evenly thaw the hamsters after they had frozen and made it more likely for them to survive the freezing process. So we have microwaves because scientists were freezing and thawing hamsters. But it turns out animals, or mammals specifically, about the size of a hamster, is about as big as you can get to freeze and then thaw them back out before too many cells are ruptured, or something to do with the size of the animal, and the freezing doesn't work out. Okay, I think my voice is pretty much shot for today, so we're not going to go over much more, but we did finish this chapter, and we can start chapter 13. Whew. Are there any questions on this chapter or anything in general? Did I miss changing the deadline for some assignment again? Chapter 12 will be due this week, by the way. Nice. Glad to hear it.